In the last session, we have seen the introduction to parallel manipulators. In this session, we will be discussing about the kinematics of parallel manipulators. So, parallel manipulators, kinematics, so it includes the direct kinematics or the forward kinematics and the inverse kinematics, right? So the direct kinematics problem in a parallel manipulator, it is a two-step problem statement wherein in step one you will be given the geometry of the manipulator and the actuated joint variables, and you have to obtain the passive joint variables. In step two, you need to obtain the position and orientation of the chosen output link, right? So in inverse kinematics problem, you will be given the manipulator geometry and you need to determine and the position and orientation of the end effector or the output link, and you need to determine the actuated and passive joint variables. So in parallel manipulator, forward kinematics is much harder to obtain. Uh, this would be the I mean inverse of what we have discussed in serial manipulator. In serial manipulator, forward kinematics, it is very easy to obtain. Whereas in parallel manipulator, forward kinematics, it is much harder to obtain, right? So generally, the inverse kinematics problem are very simple when compared to serial manipulators, right? So first we will see about direct kinematics. So in direct kinematics of parallel manipulators, the link dimensions and the geometrical parameters are known. The link dimensions and the geometrical parameters are known. The value of the n actuated joints are also known. So what are the different actuated joints in the manipulator are also known. So remember, in the parallel manipulator, as discussed in the last lecture, there will be some n actuated joints and m passive joints, right? So n actuated joints and m passive joints. So the first task in the direct kinematics of parallel robot is to obtain that m passive joints. So basically, how do I solve? For the m passive joint variables given the n actuated joint variables. So what do we need to do? We need to first obtain the minimal number of m closure constraint equations in m passive variables and n active variables. Okay, so m should be as small as possible so as to make our life simpler and easier. So then we use the elimination theory. We use the elimination theory, for example, the Sylvester dialectic method or the Besot's method, to eliminate the m-1 passive joint variables to obtain a single equation in one of the passive joint variables, and we would like to solve these m nonlinear equations in closed form for the passive joint variables. So once we find the single eliminant, we can solve that equation, and then by back substitution, we find all the m passive joint variables. So once the actuated joint variables and the passive joint variables are now known, we can obtain the position and orientation. We can obtain the position and orientation of a chosen output link from the known values of theta and phi. Okay, so recall in a parallel robot, there is no natural end effector, not like in the serial robot where the free end is typically the end effector. Hence, we have to say which one is the natural output link. Okay, so there is no defined natural end effector in a parallel manipulator. So we have to first say which is our natural output link. Most of the time it is sort of obvious, but nevertheless we have to say that this is the output link of the parallel robot. So there are no known general method as compared to direct kinematics of serial robot. Why? Because of this problem, choosing this M close loop closure constraint equations, and also to find the minimal polynomial in one passive joint variable is not always very clear and obvious. So, what is the problem statement in inverse kinematics of parallel manipulators? So, we are given the geometry and the link parameters. We are given the geometry and the link parameters and the position and orientation of a chosen output link with respect to a fixed frame. And the problem is to define the joint variables to define the joint variables. So this problem is simpler than the direct kinematics problem, since we need to no need to worry about multiple loops or loop closure constraint equations. We'll see that we can break up this problem into serial chains and uh, obtain the joint angles in each chain in parallel. Okay, meaning in parallel means the first chain and the second chain can be computed separately. So if you want to break this manipulator into chains, we have to make sure that no chain is redundant, right? In order to break the chains, we need to ensure that no chain is redundant. So remember, in a serial robot, if you have more than 6 joints in a 3D space, or if you have more than 3 joints if the motion is planar, the set of equations are redundant. Okay, so we cannot find unique inverse kinematic solutions for a redundant chain. So the worst case in the inverse kinematics of parallel manipulator is the solution of the inverse kinematics of a general 6R serial manipulator, right?